Okay. So, tell me what you observe. Everybody, what do you observe about the result? So here there are 3 results, yes?
Yes.
So for question 1, I will raise this later. Z cubed equals negative 27. So I'm going to call the result Z1, Z2, and Z3. What do you get for Z1?
3 over 2.
3 over 2.
Plus 3 root 3 over 2i.
This?
Yes.
Okay, what about Z2?
Negative 3.
And Z3?
3 over 2.
Minus 3 root 2 over 2i.
Do we notice something there?
Yes, Z.
For this, there are 4 results. Z1, what do you get?
2.
2. Z2?
2i.
Z3?
Negative 2.
And Z4?
Negative 2i.
And you agree this is 0 minus 2i?
Yes.
Why this is 0 plus 2i? Yes?
Yes.
Okay. Z to power 5 equals 32. 5 results. Z1?
2.
2.
2. Z2?
0.62.
0.62
Mhm.
plus 1.92.
1.9?
9i.
Z3?
Negative 1.62.
Negative 1.62.
Plus 1.18i.
Z4?
Negative 1.62.
Negative Z4? Negative 1.62. Yes?
Minus 1.18i.
62 minus 1.18i. Then
Yes.
Z4? Z5?
0.62.
Minus 1.9i.
Finally, Z6, negative 64. Z1,
Root 3 plus i.
root 3,
Plus i.
that's all.
Yeah.
Z2,
2i.
2i,
Yeah.
Z3,
Negative root 3 plus i.
Z4,
Negative 2.
negative, Z5, Z6, so what are the observations here? What do we notice? Yes, quickly, please. Clarissa? Then I'll come to Krista.
C1 and C3
Complex conjugate. Okay, and this stands alone. Can somebody tell me why this guy will stand alone?
Z4 will be the conjugate.
What?
No Z4. Or no.
There's no other one to pair with because it's 3. You expect 3 answers, right? That's why I wrote the first. Of course, we know it by the fundamental theorem of algebra. So if you are solving this equation, there will be n roots. Yes? In this, what do we notice? Conjugate here. Yes? But these are not conjugate, are they? I think they are. One is plus, one is minus.
Yeah. Plus 0i.
Yeah, they are. No, they're not.
Oh.
This is 2 plus 0i. This is minus 2 plus or minus 0i. As long as the real values are not the same, they are not complex conjugate. To get complex conjugate, they must have the same real. The only thing, the negative is on the imaginary.
So it's there or is it not?
No.
So they are not complex conjugates. Yes? Okay, so we can see, oh, I thought if we have even numbers, there will be pairs of conjugate and non-complex. So I think there is some kind of problem. Let's assume. Okay, here, nobody to pair with, right? And the others can, be friends, conjugate-wise. Yes? And here, everybody has a friend. Yes? Who is Krista's friend? Another Krista. Okay, and here, and this is just next door neighbor. Kind of. Are these conjugate?
Yes.
Are you sure?
That one is, that one is.
Are you sure? Why?
Because it's 0 plus.
0. They have the same 0. Then you have 2 high and negative 2 high. So they are complex conjugates. Okay? So what do we notice here? If you have this, yes. Okay, you notice never mind. That's good. Now, when you solve this, you have n root, we know that. This case, the case we did last time is this. Let's focus on this one now. If W is a real number, that's why I gave you all real numbers. Yes? What do you notice in the case of when W is a real number? Do you know what I mean by W?
Yeah.
These are your W. They are real, no imaginary. When you have real W, what can you say about the roots? Yes, sir. A general statement that works for all situations. Yes.
When the power of z is odd,
Mhm.
z1 will not have a conjugate.
What do you mean Z1? Anything could be Z1.
Well,
No, it doesn't work.
one number
Doesn't work like
will not
that.
have a conjugate.
Because in this case, oh, okay. Z1 doesn't have.
Z2.
No, but then the first one.
First one is
First
Z2.
Oh wait, never mind.
Yes. You know the answer lies in what? Conjugates.
They all at least have one conjugate.
There are certain ones that have conjugate. Look at it very well. There are certain, roots that have conjugates.
2 and 4. Wait, no.
What?
What?
What do you mean 2 and 4?
What?
If you look at question 1 to 4, there are certain roots that have conjugate. That conjugate thing does not apply in certain situations.
Apply when root is real.
If what?
The root is real.
What happens if the root is real?
There is no complex conjugate.
There's no complex conjugate. So which roots have complex conjugate? Only the complex root will have conjugate. The real root doesn't have anything like conjugate.
Oh.
This is real. So among the 3 answers, 1 is real, 2 are complex. That is why before now, if a teacher gives you x cubed equals negative 27, you say cube root of negative 27, and you say the result is negative 3. Right? That's just one of the results. We just realized there are 2 others, and they will be complex conjugates. If you look at this, this is not real, this is not complex, this is not complex. So conjugacy does not apply. But here, so basically, if you are solving with respect to your C, or the constant, which is in this case represented as W, as we have been doing since last lesson, I chose W so there will be consistency. Okay? That constant, if it is a real number, only the complex roots that are produced are complex conjugates. They are pairs of complex conjugates. When you compare this with what we were trying to observe the last time, we don't have this pattern. We have complex conjugate in some situations, we do not have in some situations. So if your W is a complex number, like the last set of activities we did the last time, not all complex roots are complex conjugate, have conjugates. Not all of them. Look at the result from last time, everybody. Okay. So look at result from last time. I'm looking at A and C. I don't know what is A and C. If you look at the answers, you will see that if there are 5 answers to be established, you are likely to see 1 or 2 complex conjugates. Some of them will come as negation of the other, like all minors, but it doesn't apply in the case of complex. That's the point I'm trying to make. So our note here, if W is not a real number, which means if it is pure imaginary complex number, not pure real number, yeah? If it is not all complex roots have conjugates. Of course, some we have conjugates, but not all of them. But in this case, all complex roots will have conjugates. Does that make sense? Can we take note of that? Is absolute value 16? Is this all you get for absolute value? Yes?
Yes.
My next observation is about absolute value. I need you to look at all the roots and see what you notice about the absolute values of your roots. Absolute value of your roots. Is there any connection between absolute value of your roots and the absolute value of W itself? Do you get my question?
Say it again.
Okay. Observe your roots. I need to see a doctor tonight. Observe your roots from number 1 to number 4. Let's pick it one after the other. Look at your Z1, Z2, and Z3. They are complex numbers, yes?
Yes.
What do you notice about the absolute value of Z1, Z2, and Z3? What are the absolute values?
For Z1,
Okay, so absolute value of Z1 is what?
3.
Okay, absolute value of Z1 is 3. What about absolute value of Z2? That's easy. That's 3. Absolute value of Z3?
3.
Okay. Is there a connection between this and the absolute value of W? Then observe the second one. Observe the third one. What is the connection?
Times them together and
Say that again.
times them together and then mix the
Well, let's see if the same applies here. Absolute value of Z1 here is 2. You agree? Absolute value of Z2 is 2. Absolute value of Z3 is
2.
absolute value of Z4 is
2.
so. What is the connection between that? Times them together. So how do I summarize it?
Absolute.
Because I'm multiplying 4 things, I'm multiplying 3 things, so I can't have a fixed thing to multiply. What is the best way to say it?
The absolute value of the roots is the nth root.
Absolute value of any root
Is the nth root.
is the nth root of W?
Of the absolute value.
Of absolute value of W. That makes sense. You understand that? Again, here, the cube root of this, because there are 3 of them, right? If you take the cube root of this, you get 3, which is the absolute value of each of the roots. If you take the 4th root of this 16, you get 2, which is the absolute value of each of them. If you take the 5th root of this, you get 2, and that must be the approximate absolute value of this. Remember, this is an approximate value. And the same applies here. The absolute value of W here is 64. If you take the 6th root, you get 2, and that should be the absolute value of each of these roots. So another observation we can write is the absolute value of the solution. Absolute value of Zi. I call any solution Zi. Okay? Or should I say Zk? Were we using K? Yeah, we use K. Okay. Absolute value of Zk is the nth root of the absolute value of W. Or we can write as absolute value of W to power 1 over n. Okay? Krista, are you lost? So these are the major observation that I wanted to discuss. The last one is about what we notice if we put all this in an Argand diagram. Let's try one of them. This may not be easily plotted on an Argand diagram unless we can get the decimal point. But let's see this that looks easier. So in an Argand diagram, 2, Z1, 2, here. What do you notice about the line of Z1, the line that will represent my Z1, Z2, Z3, Z4?
They'll all be.
They will all be?
The axis. Right on the axis.
No. With the length of the line, let's put it that way. The same. Because they all have the same absolute value, right?
Yes.
So this represents my Z1. Z2, positive axis, yes?
Yes.
The same length. Z3,
Negative 2.
negative of this one, yes? And Z4. Maybe we don't notice something yet. Let's try any other one, maybe question 4. This is question 2. Let's try question 4. Can we see here? In question 4, root 3 is 1 point what? Give me an estimate. 1.7, 1.5, 1.7. So x is 1.7, y is 1, sort of, something like this. With the same length of line in each case. Z2, 2i. 2i will be here, the same length of line. So I have something like this, I have something like that. Z3, negative 3, negative root 3, the same length here. So it's going to go like that. Yes?
Yes.
Then Z4, just like the mirror of this one. Yes? Then Z5. So basically this is an extension of this.
Yes.
Do you agree this is an extension of that?
Yes.
Then the last one is also that. It's not drawn to scale, but is it possible you deduce something from here?
You only need half.
What?
You only need half.
What do you mean half of?
Half is the measure of
I didn't get that.
the reflection.
They are a reflection of each other on either x or y axis. What does that tell you about the angles between them?
Same.
Same. Which means they spread out evenly. This one also, this is obvious, right?
Yeah.
90-90. Now, because they have the same length, what do you notice will happen if we try to connect the position of Z1 to Z6 or Z1 to Z4 together? This is what I want to show you on the software, but unfortunately I've not been able to see which software explains this better. But maybe we can visualize it on the board. Now, this is Z1. Let's say this is Z2. I don't know which one is 3, 4. If you connect Z1 to Z4, what do you notice? If you connect Z1 to Z6, what do you notice? I don't want to connect. If I connect it, I tell you the result already.
What do you mean, like connect? You draw a line?
Yes. What? Can we see this spot?
Yeah.
Okay.
Is it the angle of?
We've already talked about the angle.
No. I mean, like when you connect the,
Yeah, and I saw solution.
when you connect all the points, the angle of the shape is the power of the.
The angle of the shape. That number of angles in the shape. Definitely. Oh yeah, definitely. That's a point. Good. That's a point. So this is Z1, Z2, Z3, Z4, Z5, Z6. What do you notice if we connect that? Somebody was saying something. I don't know if from here or from there. Or maybe from here. What?
It's going to make it like a regular shape.
A regular shape. You're going to end up getting a regular shape. So in this case, because there are 6 of them, what shape comes out?
Hexagon.
A regular hexagon. Here there are 4 of them, you have a regular quadrilateral. And what is that called? A square. How do you know this is not a rhombus?
It's the same as
We don't call it length.
modulus.
No. I'm not talking about complex number, I'm talking geometrically.
The sides are the same.
Of course, we know that. For a square, the sides are the same. For a rhombus, the sides are the same. So both square and rhombus are equilateral. But both of them are not regular. They're two different things.
At the same angle.
They have the same angle.
Internal angle.
Is that what makes it regular? What is a regular shape? Let's talk about
Same
it.
length and same angle.
Same length and same angle. Good. So from that, can you tell me why this is not a rhombus?
Because same length, same angle. Rhombus is a pair has same angle.
But they all have same length, but two opposite angles are equal, but not all the angles are equal. And that's because a rhombus is not equiangular. To qualify the title of being a regular shape, two things must be met. One, all the lines must be of the same length, or the angles must also be of the same measure. So we say a regular shape must be equilateral and equiangular. Do you get that? Equilateral and equiangular. If one of these two is not met, it is not regular. It becomes irregular. Give me an example of a shape that is regular but not that is equilateral but not equiangular. Equilateral but not equiangular.
Parallelogram?
Parallelogram. Is it equilateral? I don't think so. Parallelogram looks like this.
Oh, right.
Oh, star.
Can we not go? Let's discuss simple shapes like 3 sides and 4 sides only. Please. Equilateral but not equiangular. What kind of triangle? Because I can give you a triangle that meets both conditions. Irregular. What do you mean irregular triangle? Isosceles triangle.
Irregular.
That irregular is a way of cheating. He's trying to cheat me.
Isosceles have same side?
Equilateral but not equiangular. No! I'm so sorry. I was thinking of something else. No, that triangle doesn't give us that condition. It's irregular, but it's not equilateral. Can you think of something equilateral, not equiangular? I've mentioned something today. In fact, you mentioned something today.
Rhombus.
A rhombus.
Oh, God.
That was the one I was expecting from her. I just clicked. I just told her yes. Okay, let's twist it quickly, please. Equiangular, but not equilateral.
This can be the same like this.
Wait, Randy. Sorry.
What?
Equiangular, but not equilateral.
Equiangular but not equilateral.
Triangle, rectangle.
No.
Wait.
That's it?
Yeah, rectangle, yeah. Same.
Rectangle works. Okay? So equilateral, but not equiangular, we can talk about rhombus. Equiangular, but not equilateral, we can talk about rectangle. Equilateral and equiangular. Give me 2 examples. Square, equilateral triangle. And there are some that are neither equilateral nor equiangular. Then our answer comes in. Yes, isosceles. And one other triangle. Irregular triangle. What? I can give you a right angle triangle that is equilateral. Yeah, okay, no equilateral. Yes, we can. In either equilateral, yes, any right angle triangle will work.
Those random triangles, you know.
But the general name,
What is it called?
scaling. That's what I was looking for.
Oh, that's called scale.
What is here?
Scaling means not all the sides are unequal.
For what? Any shape?
Any triangle.
Or any triangle?
Okay, so what is it? You want to take a picture? Oops.
That one is fine. Just take a picture of this. Yeah, this is okay.
Yeah, this is easily seen.
Yes.
The first one is easily seen. So we have 2, 2. So this is 2, this is negative 2, this is 2i, this is negative 2i. So you can take, okay. So the last thing to write here is what we have just said. On the Argand diagram, maybe I write it. Have you taken it? This and this, because I want to take one of them out. Oh, yeah, I want the observation to be to follow. This is the first picture we need. Then, based on this, then we can now talk about this one. Have you taken this? Okay, I can take this out. Let's quickly write the observations. Okay. So, of course, we have more practice to be done. We just move to the last part of the roots, which is about unity. Unity means one. So it's simply just like what you have done, because one can be any of this number can be one. The only difference is that we don't have absolute value. Not that we don't have it, but because the absolute value is 1, so it doesn't appear. And also, what can you say about the argument this time around? If you're looking for this, maybe root of unity. So the arguments will either be 1, 0, or pi, depending on if we're talking about the positive or the negative. Yes? A formula will become reduced, basically. So I'm going to write the nth root of unity. The nth root of unity. So by unity, we're talking about 1. Okay, I have a question. I might have mentioned this before, even in the previous grade, for those of you that have had 1 or 2 classes with me in the past. Numbers, let's say integers, can be, should I say integers? Let's go with just natural numbers. Okay, positive integers. Positive integers can be grouped into 3. Does anybody have an idea mention any group that you think numbers belong to? Prime is one of them.
Square.
Square. Okay, square. You see, these 3 groups that I'm talking about, integers, no decimal, so there's no fraction. These 3 groups that I'm talking about, they are disjoint. Do you know what I mean by disjoint?
So they won't have here.
They don't have anything in common. Okay? So these 3 groups are disjoint. The combination of these 3 gives you the entire set of natural numbers. One of them is prime. That's right. Can you think of the other 2? What? Even, no. Okay, what would be the third one? If there's a way, okay, if you say maybe even, I guess the next one would be odd. But remember, odd and prime are not disjoint.